And the title of his talk is Why Green Hydrogen Matters.
Yes. Good morning. First, I need to thank Alexandre, Danilo, and Inés for the organization to invite me to this event here. And today I will talk about the hydrogen. So a topic is very it's common for physicists, right? Because we usually study hydrogen in quantum mechanics, but also in this case is uncommon because we will talk about molecules and catalysis for production of hydrogen. So first, I need to thank my research group, right? The students, the funded agencies, and the computational facilities for the NACADE. And in July this year, the NASA released some photos of this James Webb Space Telescope here, and so you can see they have a lot of photos, but one thing that the people usually don't talk about this is because of these photos, not only the cloud but all the stars. Usually, you have about 74% of this is hydrogen. So not only for the one star, but when we talk about all the things made by atoms, usually are in large part hydrogen. And not only the universe, but our sun too. But we have 75% of hydrogen. And here we have talk about on Earth. We have about 11% of the hydrogen. 11% of the ocean is hydrogen. When we talk about mass, and about 10% of the human body is about hydrogen. But when we talk about this, you usually talk about the mass, not the quantity of atoms. And why we have this percentage about 10%? Usually the hydrogen is bound on molecules like water and organic compounds. Here I'll show you ethanol. And in very hardly we can find the H2 molecules. So in mass we have about 30%, but in quantity of atoms, right, we have a much higher constant. The quantity of atoms is very high. But usually we think we can find a lot of hydrogen in water, organic compounds, but not so much in H2. Why we can find so much H2? The reason, because we can find it's very hard to find this, is because of the chemical potential. So we talk about the chemical potential for hydrogen in H2 is higher than the chemical potential in water and the organic compounds. So when you have this compound like H2, is actually we have we can think about like two steps, like in water and the H2, and this in H2 have like a higher chemical potential. So actually we can think about the more stable phase is actually in water or in or organic compounds, but we can think about the H2 to store the energy. So if you have a higher step here, we can think about the H2 to store energy in a very effective way, because we have with a few mass we have a lot of we can store a lot of energy. So we compare this with some fossil fuel based methods to store energy, like coal and gasoline. The hydrogen is about it's almost 3 times higher for to store energy than when you compare it to the gasoline. So even with the we can talk about this, and for when we talk about this energy density for gravimetics, so divided by mass, it's very low when you compare divided by volume, but it's not a problem. Usually this is not a problem because we can store this at high pressure. And we can to convert this chemical potential, we can convert this chemical bonds in current, in electricity, using a fuel cell. When in this case, the hydrogen react with a catalyst in one side, one electrode, break the bond, and form the water molecules, and the electron go outside and release like electricity. So, but for this, we need to talk about hydrogen production. Today, usually we produce a lot of hydrogen using methane and coal. So for the 50% of hydrogen production in the world today is based on this method with methane reforming. So, but in this case, we can see here this method release a lot of CO2. So it's not a renewable way to produce hydrogen. So, and we needed to think about more, like it's a green way to use in vehicles, but it's not so green in this case for hydrogen production, right? And another way when we talk about green hydrogen, we produce hydrogen based on the water splitting, so the electrolysis of water. We have a device, electrochemical device called electrolyzer. It's similar to fuel cell, but in this case we need the energy to store the energy. So we have in this case here, the water is breaking and is split in the hydrogen part and oxygen part here, and the energy is stored in this case in the hydrogen bonds. And we have this equation here for the one anode, the cathode and anode here, and the overall equation. Oops, sorry. And one part of this equation, this reaction, it's called the hydrogen Evolux reaction, and we have some steps, like a volume step, and in this step the hydrogen is absorbed in the surface, and the following steps is a hydrolysis or step equation. Here is another step, and this step we can combine the hydrogen absorber hydrogen to form two absorber hydrogen to form 82, or one absorber in another from a solution to form this 82. And this is a very crucial step to produce hydrogen here, and we need to start this part of this absorption of hydrogen in the surface of some metal here. So we have what we call hydrogen color code. Here I'll talk about the gray hydrogen. It's what we call the gray hydrogen is the hydrogen produced by fossil fuel methods, like methane and coal. Blue hydrogen is like a similar, but we have a carbon capture and storage and utilization for this carbon capture here. And green hydrogen is this case we have the electrolysis of water and no CO2 emission. Actually, I'm showing here three, but have more and more some colors. For example, we have some people call the white hydrogen that produced naturally, and pink hydrogen by nuclear reactions. So have a lot of color code for this hydrogen here. And but we have some problem here, because to produce this hydrogen, we have a catalyst. One for cathode have a platinum cathode, and for anode we have iridium oxide anode. So we have a very hard metals here. Right? So if you think about the abundance of these metals in the Earth, you can see the platinum and the iridium is the hardest metals here. Iridium is the hard metal in all the periodic table, and you need So platinum is very expensive and very hard to, and only one country, only in South Africa, is produce the platinum here. So we can think about this is not scalable for the large if we wanted to do this large scale production of green hydrogen, we need to think about other metals or use less hard metal. Or even if maybe we can still use platinum, but few platinum. So. And for discovering of novel catalysts, so we can using ab initio calculation and calculate this Gibbs free energy for the for hydrogen absorption, and we can calculate here this semi-classical part for hydrogen absorption, quantum effect for this hydrogen absorption. In this case, because of the hydrogen is so light, we need to consider the one correction for the quantum. The quantum nature of the proton in this case, and in this case for temperatures and difference of entropy for hydrogen absorption and absorbed and not in the in O2 82. So in this case, we don't have a pressure and volume because it's very small. So I'm not considering the pressure. So when you calculate this, we have a principle called the Sabatier principle, because in this principle we can see this the catalysis for hydrogen production for hydrogen evolution reactions is optimized when we have delta G is very close to 0. So in this case, like here, we have the calculation in this x axis here. We have a delta G calculated from the ab initio calculation, and the y axis is experimental data for this. Sorry, and to reduce to do this catalysis, we need to think about the surface area for the catalysis here, and so it's a very common use nanoparticle and reduce the size of the nanoparticle. When we reduce the sizes, we can see here the number of atoms exposed in the surfaces increasing. For example, for 5 nanometers nanoparticle, in this case this is cosahedral particle, 28% of atoms are under the surface. But when we think about the 1.4 nanometer nanoparticle, 76% of the atoms are on surface, and this is important because catalysis is a surface effect, and so we need a high surface area to do this catalysis, and also because we can think about this divided by the masses and divided by the quantity of the platinum or iridium you will use, and if you think about the nanoparticle, we can increase the part of the ratio for the catalysis divided by mass. And the Mackenzie where I work, we have we did a collaboration with the experimentalist, and they synthesizes some particles, different nanoparticles. In this case, gold and a core shell nanoparticles is a gold core and a platinum shell. And in this case, we can see they synthesize the particles very small, smaller than 2 nanometers, using the chemical methods on the graphene oxide substrate. And we can see here from the microscopy here, you have a lot very small nanoparticles. In this case, we can see also they have some lines. This image was made on the LN Nano here in Campinas. And you can see the lines. It is atomic lines. You can see there's not. You can see the patterns for these lines in this here in this nanoparticle. And when we calculate the electronic properties of these nanoparticles. But one thing when we compare is the delta G. In this case, is delta G. And in this case, I will compare for our core shell nanoparticles. Here, I have about this 0.09 minus 0.09 electron volts, and this is better than the pure platinum nanoparticle with this similar size and similar shape. And we compare this with this as the initial calculation, and we can see the experiment. And we have also we can compare this core shell nanoparticle have this catalysis better for when we compare with this platinum nanoparticle. And another method to do this is we can use biomimetics materials. In this case, biomimetics, how the hydrogen is produced naturally. We can see some bacteria have some this nitrogenase protein, and this protein have some inorganic part. We call this iron molybdenum cofactor, and this iron molybdenum cofactor have this part here, this active part of this this protein to produce hydrogen, and the people looked at and think about this. Oh, this is similar to the edge of MeOS2 on a two-dimensional material. So they proposed the material like MeOS2 on a 2D material and use the edges of this material to produce hydrogen. And see with different parts, different sizes of these nanoparticles, the catalysis is scaling with the length of these particles. Another strategy is use the effects, like intrinsic effects, like sulfur vacancies in MeOS2, and phase transition of this 2H to 1T phase, 1T, actually 1T prime, because we have some distortion in these letters. And when we have this phase transition, the material converts from semiconductor to a metal, and this metal is very, the catalysis is much better than the basal plane of MeOS2. So one of my PhD students did some calculation with a similar, not a MeOS2, but we proposed to study not only another disulfide, like a palladium disulfide, because we have also we have two different phases. In this case, the pentagonal phase and the 1T phase. The both phases are semiconductors, different for the MeOS2. We have MeOS2 have a semiconductor phase, a metal phase. In this case, we have two different semiconductors, and we did some calculations with DFT calculations with these different phases, and studied the effects in this material too, like sulfur vacancy, palladium vacancy, devacancies, substitutional defects, and interstitial defects. And I'm showing here the defects for the pentagonal phases, but we have similar defects for the 1T phases. I'm not showing the 1T because it's very similar, but we have this kind of defects here. But I'm showing the formation energy. We can calculate the formation energy for these defects in the PDS2. In this case, I need to think. I need to highlight some things here, because, for example, different phase in the left side have a pentagonal phases, defect in pentagonal phases. In the right side have defects in 1T phases, 1T phase. In the pentagonal phases, the lower formation energy is for interstitial sulfur, but for 1T phase, the lower formation energy is for sulfur vacancy. So it's different, very different defects. So here one have one sulfur vacancy more than here we have one sulfur vacancy less than the usual, right? And we have these very different effects in the two phases here. And when we calculate the hydrogen absorption on the defects, we can see here first we compare with the pristine material, so no defects here for the pentagonal phase and 1T phase. The 1T phase have a smaller delta G, so it's better than the pentagonal phase. But when you compare it with this defects here in pentagonal phases, all defects increase the catalysis for the hydrogen production, but not for the 1T. 1T some have some palladium vacancies or palladium interstitial have worse activity for the hydrogen production. And for in this case, the best effect for the hydrogen production usually is sulfur vacancy here too, right? So like MS2, in MS2, the sulfur vacancy is the best effect for the hydrogen production reaction. And in this case, we talk about the PDS2. In both phases, the sulfur vacancy is also the best effect for the hydrogen product reaction. Even in one phase, it's very common effect. In the other phase, it's not the most common effect. So in this case, I need to talk about some contributions we did. So this paper published also by this PhD students. We have all the opponent effects increase with the catalytic activity for the hydrogen product reaction. In the sulfur vacancy is need to highlight two things: is the lower formation energy, so it's the more common effects, and this higher catalytic activity for hydrogen evolute reaction. We did have this here is the calculation. We don't have this experimental data for the PDS2 yet. We need to talk more with the chemistries to synthesize the material, to do some phase transition, because here at Mackenzie we have a very good chemistry group producing MS2 and do some phase transition with MS2. So we can do it. Maybe we can do this with PDS2, but we don't have the experimental data yet. But it's we need to talk about more with the experimentalists to talk that. But one thing I need to highlight here is what we can learn from this material, right? Even if we talk about not only one material, but what we can extend, what we learned with MS2, we can extend for PDS2, and what we can extend for another semiconductors based on the transition method dicocogenide or transition method disulfide, right? We can see that they have some patterns like sulfur vacancy can increase the catalytic activity. It's not a special case for molybdenum disulfide. Maybe we can extend for more transition method dicocogenide, like with different phases, with different symmetries and different formation energies. We still have some similar patterns here. So this is what I'll talk about. So thank you.
Thank you. Questions?
Hi, Leandro. Thank you very much. It was a great talk. So just to see if I understood correctly, when you mentioned on catalysis on dichalcogenides, you mentioned about edges and defects. Are these the regions where you see higher catalytic activity? And like, for instance, in edges of small islands, is that correct?
Yes.
And why this happens? Because of the presence of dangling bonds or something like that? I think I missed this point.
Yes, we have a correlation with the edge length with this hydrogen evolute reaction, and actually it's because of the bonds of this the molybdenum exposed. But even different edges have a similar. In this case, we have different edges, but with high activities too. So it's not only the dangling bond. It's maybe as it's a collective effect for the edge.
Okay, just one more quick question. So the defects that you consider are all neutral, or you
Yeah, in
look
this
at
case, for defects into the materials, we need to calculate neutral defects because it's very hard to calculate the formation for charge defect in 2D. It's not. We have to do some correction, and this correction is not so easy to calculate.
That's what I was going to ask. But do you expect some like very different results if you consider ionized defects or not? Thank you.
Maybe I think the charge defect will decrease the formation energy and the occurrence of this defect. But I don't know if you can extend this for the Gibbs free energy for hydrogen absorber. Maybe the occurrence of the effects will be very different in this case.
Further questions? I have a quick question. So maybe I missed this, but can you understand why from one phase to the other, especially the interstitial sulfur has such a change in formation energy?
Why you have this interstitial sulfur? So
yeah, I mean the change is more than like
yes, it's very different because yes, in this case I think because the geometry of the defect, the material is very different, and when you think about this, let me show here. In one T phase, all the sulfur atoms are bonded with this palladium, but in pentagonal phase you have this sulfur bonds, and because it's this pentagonal phase, so we have a different bonds. So if you include one more, sulfur is very different to include with sulfur bonds here and sulfur bonds here. Is very, so in this case, we will be very different because of this. The bonds here are different. We have a sulfur here when we don't have here.
Thank you for the talk.
Oh,
did you use some gap correction method, or how it will affect your results? What do you think?
No, all the band gap calculated are with PBE in this case, but for this material, it's not so bad. For when you compare the PB band gap with experimental band gap, it's very similar. It's not so. We can do calculation hybrid functional, but maybe we have a correction of 0.1, 0.2. But in this case, I think it's not. But in this case, we can calculate for pristine. But for defects in the supercell, it's not so. It's a very expensive calculation, so we prefer to study only at PB level here.
Just congratulations, very hard and very beautiful work. And however, can you just tell us how do you introduce this just an experimental answer to an experimental question? How do you introduce these vacancies or interstitials in the? Is it easy to do that?
Yeah.
Would it be easy to do that experimentally?
When we study the MS2, we usually do the separation of of MS2 with the Alessio intercalation, and with intercalation they have a phase transition, and when we have the phase transition, we include a lot of defects in this material. So experimentally, when we see the material, we have a lot of defects in this case. But it's actually the hard part is not how to not do the defect. But what the kind of defect we can calculate the occurrence of the defects with the formation energy. So you can calculate. Okay. And another defect, another method to do this is with CVD, so chemical vapor deposition. So in this case, the material is growth in the metal, and with a very low process, we can do the material with a very good quality, and but in this case, it's not so but we still have a defect. For MS2, in this case, for MS2 have a high hydrogen catalysis, hydrogen evolution reaction catalysis, actually they do also the oxygen plasma beam to increase this defect, because for MS2 we need to have a 25% of defects. The amount of the defects is very, very high. Actually, you destroy the material to increase 25% of the material. In this case, we talk about here is about 1%, 2%, 3% of defects in the supercell. But for MS2, you need to increase much more. And in this case, use oxygen plasma beam instead on the material to increase the quantity of defects.
Okay, let's move on. So let's thank Leandro again.
Thank you.